So evolution, the simplest definition of evolution is gradual change. Evolution simply means that things change over time. Through the 19th century and by the 20th century, evolution becomes the guiding explanation for the world and life. The breakthrough in evolution really came in geology, the study of the earth, by geologist James Hutton, an Englishman at the end of the 18th century. He wrote a book called The Theory of the Earth. And he challenged some of the prevailing ideas that fit with Scripture. Right? Other 18th century geologists were willing to accept a cataclysmic or catastrophic geology. That the world was formed, but that every once in a while, there was some major catastrophic or cataclysmic event that changed the basic makeup of the world. An earthquake, a volcano, a tsunami, right? People knew about these events. A flood. And so for other geologists, other than James Hutton, the world was fully formed and created, but that every once in a while, there was this catastrophic or cataclysmic event. So hopefully you can understand how this would fit in with biblical stories, right? The biblical story of the flood, the biblical story of Sodom and Gomorrah, that every once in a while, these events happened, and biblical scholars would say, that's evidence of God being mad at humans. These geologists, right? These geologists other than Hutton, also argued that there were receding oceans, that the oceans were dropping gradually. Once again, this meets with the flood story, that everything on the earth was flooded, and then God gradually drained that away. So when geologists would go out and look, they would say, look, we found seashells on the top of a mountain. How could those seashells be fossilized on the top of a mountain? And the answer to them, well, this would obviously explain that there was a great flood. The waters receded and left dead animals, right? Dead marine animals on the tops of mountains. This would be a logical explanation, right? So these scientists in the 18th century were matching their observations with what they found in the Bible, and they would find no contradictions. Hutton, on the other hand, started seeing something different. And he provided a new way of looking at geology, the makeup of the world, or explaining the world. And that new idea is called strata. That the Earth's crust is composed of strata, levels. And that mountains come from uplift. That mountains were once on the floor of an ocean, and through a process called uplift, they are taken from the bottom of an ocean and moved to the top of a mountain. In other words, there was no, quote, great flood. That somehow the Earth's crust itself was moving around. So if we imagine, right, a big mountain right here going off into oceans on either side. Above that mountain, you have things like clouds. Clouds have precipitation that come down. And what does that falling snow, ice, rain, water, what does that precipitation do to a mountain?
Erodes it.
It causes erosion, right? Which means you're going to take some of this mountain and you're going to move it down in a river, and it's going to start depositing on the bottom of a lake. Right? Hutton was the first to notice these strata and come up with an explanation of what was going on. So if you look at something like the Grand Canyon, you can see the various strata, the different colors, right? All the different colors are different historical events that happened in the life of Earth at the Grand Canyon. Hutton was doing this in England, right? And then he noticed, right, that for how did the mountains get there? Well, one part of the Earth is moving this way, and one part of the Earth is moving this way. And when they collide with each other, they either come up like that, right? Or one goes under and one goes up. But no matter how this happens, the revolutionary idea that Hutton introduced to geology is evolution. The Earth itself, the crust of the Earth, is constantly evolving through a process of uplift, through a process of erosion. These are small changes over time. Yes, there are big things like earthquakes and volcanoes, but they all fit into this larger concept that the Earth's crust is moving through a process of creation and destruction. Now, if we fast forward into the 20th century, what's the 20th century version of this? How do scientists see the world differently? Geologists see the world differently because of what Hutton proposed. Has anybody ever heard of Pangea?
Yes.
What's Pangea, Emma?
The idea that all the continents were once together and then drifted and separated apart.
So how long would it take Africa, for example, to drift apart from North America? Like 5 days, 10 days?
A lot longer than 10 days, I'm assuming.
Yeah. We're talking about millions of years, right? So the 20th century application of Hutton is the idea of tectonic plates. Tectonic plates. Teutonic would be the German knights and the Baltic region. Tectonic plates that we can look at the world as it is today and see how if you reverse that movement, there was a Pangea. But the big story here is there wasn't just one Pangea, there were multiple Pangeas. Scientists can look at not only the shape of North America and South America and Europe and Africa and see how they would fit together, but scientists could look at the geological remains on one side of the ocean, geological remains on the other side of the ocean, and see fossils that match up, see that the Appalachian Mountains actually stretches all the way to Scotland. But when scientists were coming up with these ideas, right, when they were looking at this, they didn't have as much evidence as we have today, because in World War II, when the military wanted to map the ocean floor, a scientist working for the military, this is a story about a woman, right, that it was asked earlier. She discovered the Mid-Atlantic Trench, the spot at which one part of that tectonic plate is moving to is going towards Africa, and another is coming towards America. One cannot do modern geology with a traditional idea that the world is static. Evolutionary geology is central to doing geology in the 20th century. William Smith knows about this, right? William Smith was a biologist and started putting his biological research in the context of a changing geology. And so Smith started playing with the idea of the age of the strata. And he made a very simple observation that the rocks at the bottom of strata are older than rocks at the top of strata. This is a general pattern. That naturally, using simple forces like gravity and the way things stack up, one can, by and large, find older things at the bottom and newer things at the top. And so William Smith started going out and looking for fossils. And then when he arranged those fossils, he arranged them based on depth. Right? He would group the fossils he found based on the depth at which they appeared in the strata. Right? Instead of just taking all the fossils from wherever they got and put them in a big pile, he started categorizing them based on whether they were far below or up top, and then he would record which strata he found them in. Through this process, then, he was able to start a chronology of the age of fossils. When did certain types of fossils start appearing in the Earth strata? And what he recognized is that fossil forms, life forms, or what we call species, right? Each form is a distinct species, that the fossil forms change over time. So this is a very simple scientific question. If creationism were true, what would someone find in the fossil record, right? So if creationism is true, then what would you find? Or if evolution is true, then what do you find?
If creation was true, you'd find all the fossils on the same layer, right?
If creation, you find all the fossils on the same, or at least similar looking fossils, right? That you would find human bones down with dinosaurs. But if evolution is true, you're going to find what William Smith found, which is life forms change over time. So this is the beginning of the 19th century. This is around 1800. William Smith is working, and he makes this observation. He publishes it, right? And which means he puts it out there for discussion and dispute. And since 1800 all the way till this day, scientists, right, archaeologists, paleontologists, anthropologists, I mean, all the people that are out there digging in the dirt have been pulling up fossils all around the world, and time again, which of these two hypotheses do scientists confirm? Do scientists find that fossils remain consistent or constant through the fossil record, or do scientists find that life forms change over time? What do you get in a biology class? So the world of biology and geology merged together at the end of the 18th century in this revolutionary assertion that life forms change over time, that the earth changes over time. What this means then is that European intellectuals put aside biblical creation stories because they no longer conform to what is observed and what is measured and how people understand the world. And so the vast majority of both religious and secular thinkers move away from the idea that life and the earth is a fixed design. This guy takes it a step further. He was a biologist, he was a Frenchman, and his name is Cuvier. Baron Cuvier was looking at fossils, right? And he introduced what we call comparative anatomy, where he's going to look at one set of bones and compare it to another set of bones. He's going to look for similarities and he's going to look for differences. He's going to do a compare and contrast. And he's not just going to do it with, oh, well, that one looks big and that one looks small. He's going to do precise measurements. He's going to record those precise measurements and then look for patterns. What Cuvier discovered was the idea of extinction. So here are Cuvier's drawings of two different jawbones. The jawbone on the top is what we would call a mammoth and what he called a mammoth. The jawbone on the bottom is a contemporary elephant. And so Cuvier goes out and he looks at the fossil record, and right, these are fossils. This is the shape of a jawbone of a mammoth. And they're not all exact, but they fit a general pattern. On the other hand, this is the shape of an elephant that would be alive in the 19th century. And elephants that are alive in the 19th century all fall into this general pattern. But if you compare and contrast the two, right? He found no evidence of elephants that were alive today that had this shape. And he found no evidence that in the fossils that the shape of a 19th century elephant were found in the fossils. So if you're just looking at it, right, obviously you're not going to measure it, but if you're just looking at it, what are some general observations that you could say about the shape of a modern elephant that is different than a mammoth? If you just look at them, what things just pop out at your eye if you're going to do a compare and contrast?
More defined V in the middle.
So there is a more defined V in the middle, right? So if I just draw that there, it goes like this versus this is more of a U. What goes in here on a jaw? What fits right there?
Their teeth.
That's where teeth go. So what can you say about the teeth cavity or the tooth cavity? Is it teeth cavity or tooth cavity? I don't know. Anyway, so what can you say about that cavity when you compare the mammoth to the elephant?
The elephants had more space for teeth.
Obviously, elephants have more space than teeth. There you go. So once again, this is how science works. You go out, you collect the evidence, right? Then you lay out the evidence and you start looking for patterns. What Cuvier discovered was very simple, that there were species that appeared in the fossil record that did not survive into the world we have today. This is the idea of extinction. Until Cuvier makes this observation, Europeans, humans around the world had no concept that species evolved and that species died off and new species took their place. But once Cuvier makes this assertion, right, he publishes it, other scientists can go out and they can look and they can try to find evidence that either contradicts or confirms. And what Cuvier then asserted was a very simple concept, that similarity of current species depends upon depth. That in the fossil record, fossils were more likely to look like life today if they were newer in the fossil record than species that are older or deeper in the fossil record. Those species were more likely to be different than life today. Now, there are some species that change very little over time, like sharks. But they still change. Crocodiles, right? There's a long history of crocodiles. They're very ancient life forms. But even they, sharks and crocodiles, do change over time. And that change, right, the difference in the life form, in the species, depends upon how old it is. In other words, Cuvier confirmed, right, through his separate studies, what both Hutton and Smith had been asserting in the previous generation, that life forms, that species change over time. So by the time you get to 1832, there is no scientific debate about the science of evolution. Evolution is considered a scientific fact. Life forms change over time. No longer controversial. So within about a 40-year window, the world of biology and world of geology is completely uprooted. Geologists and biologists no longer look at a fixed design, a static world. That observation and reason produced a different way of looking at the world.